Hey y'all, welcome to my ridiculously hot office for another round of physics. Yes, you heard it right, another round of physics. Let's go at it. Here's another classic example that tends to be worked out quite often, is what's called the current carrying loop. And just as it sounds, imagine that you have a circle which is carrying the current. And even more specifically, I'll say for the moment, we want the field point to be over the central axis of the circle. Okay. You say, well, what happens if you go off center? That is for Phys 332, or maybe even higher than that. Okay. So we're going to deal with this basic geometry right now. And if you want to get into more of the nitty gritty details, then come back to E&M. So we want to know the magnetic field of a current carrying loop. And yeah, we better make sure that we set up some nice axes. So I'll do X, Y, and we'll do Z out of the board. Okay. Not that we have a choice. Once we choose two, we're forced for the third. And let's go ahead and run through our process. Okay. You got it? We'll go ahead. Let's get us to the integral equation. There's a couple different ways we could go at this. Let's go the long way, and then I'll show you the shorter way. Okay. So let's start with this. We need to get the position vector of each of the sources. Okay. So in other words, take this ring. We want to take this wire, and we need to chop it up into tiny little sections. Okay. Each section being a segment of DL. So we need a position of each of those. Okay. So what I will do, let's go ahead. I am going to do this not in Cartesian coordinates, but I am going to do this in polar coordinates. Because let's face it, we have a circular object. Cartesian coordinates are not the best for circular objects. Polar coordinates are. And how I'll describe the position, again, this is, we'll say that's the x-axis and the z-axis is this way. How I'll describe the position is the radius of the loop. And then now I got to work on this for a second. So my x position, say right here, if my angle, what I call theta, so I'll call that angle theta. If my angle theta is 0, I want x to be large. So that means that I need cosine of theta here, 0. And that must mean that this one is sine of theta. Okay. Now, I always forget if I need any negative signs. So let's think. If theta starts off at 0, so when theta is equal to 0, I get 1, 0, 0. Okay. Good. Which would describe the little segment right here. Now, as theta increases, as theta starts increasing, I expect my x component to drop and my z component to get more negative. Is that what happens here? My x component certainly goes down. 1 is as large as it could go. But my z component becomes more positive. Right? You see that as theta increases to pi over 2, my z component becomes more positive. Okay? Which means I don't actually have the situation that I've drawn. I'm not circulating this way. I am circulating the opposite way. This expression I have right now is having me go this way around the circle. I don't like that. I want to go in the direction that the current is flowing just to keep my mind straight. I want to go this way. So what I'm going to do is add in a negative sign. Okay. That way, now as theta goes to say something like pi over 2, let's check this. I get 0, 0, And sine of pi over 2 is 1. And then I have that additional negative sign, so I get -1. And so at pi over 2, I'm located back here on the back side of the loop. So I think I'm going to use this. Okay, those are just sanity checks to make sure that I've written everything down right. I don't have these memorized. I haven't worked this out in advance. Okay, so I'm doing this off the cuff because I don't want it to be overly prepared. Oh, Greg, he always no. Like you have to check yourself constantly, even later on. Okay. So we have the position of the source. We need the position of the field point. Well, that one is just, we'll call this distance again just y. And so we just have 0, y, 0. Which means our relative position vector, right? We have our relative position vector is given by something like field point minus source. So I have something like r cosine of theta. Better put that negative sign in there. Y, comma, r sine of theta. Cool. Okay. Good so far? Cool. Well, while we're at it, we're going to have to figure out the vector for dl. Right? We're going to need that dl vector in order to perform the cross product. Okay. Now notice, how does the direction of dl compare to the, well, for lack of a better term, if you think about the trajectory of the current as being this circle, how does the direction of dl, how would you describe the direction of dl on that wire? That's the best way to say it. If we were on an overhead view, so if we're at an overhead view and the current's running counterclockwise, and I look at this small segment, say right there, what direction is dl going? You'd say, oh, dl's going this way. Well, how about if I looked at a little section right here? dl's going that way. How about right here? dl's going this way, okay? Do you notice, how about right there? Notice that dl is tangent to the circle. Right? Much like if the position, if you have, say, a ball and a rope attached to it and you're swinging it around your head, if you remember, the position of the ball is described like this. And if you have the position of the ball, how can you get the velocity of the ball? You take a derivative, right? Yeah. So you can kind of think of the same thing here. Okay. So this one I'll walk you through a little bit. So let's do it geometrically. So let's do this overhead view for a moment. Okay. And let me get rid of all these other ones here. Let's take a look at this dl for a second right here. Okay. Now we called this the x direction. This would be the y direction. Excuse me, z direction. So this is x, that's z. Okay. And we called this right here, this is what we're calling theta. Let's go ahead and just do a little bit of geometry to figure out what the direction of dl is. Keeping in mind that this is perpendicular to that. So those two purple lines are supposed to be perpendicular. Okay. Well, You probably already are ahead of me. Okay. So what I'm going to do, let's go ahead and draw in a line parallel to the x-axis. And if this angle is theta, that means this angle is also theta, right? Two parallel lines. What is this? Opposite angle? Not opposite angles, but I can't remember. Okay. You have a bisector of two parallel lines, so the opposite angles are the same. Okay. Well, because of those two purple lines being perpendicular, that means that this angle right here must be pi over 2 minus theta. That goes right there. Okay. So now we have an angle that can help us describe the direction of dl. We have something that tells us that our small line segment is directed, let's see here, well, let me redraw that triangle here so that we have it a little more clear. We have dl going this way. We have pi over 2 minus theta. So we have to go in the negative x direction and in the positive y direction. So the direction of dl is given by negative cosine of pi over 2 minus theta, comma 0. And then we're in the negative z direction. So I better put sine of pi over 2 minus theta. And again, we're coming up with an expression for dl. So now I'm just going to put dl here. Good so far? But wait, there's more. This is a double angle. And I tell you, I encourage you, there's no way for me to hold you accountable to this. Okay? If we were doing in-class exams, I'd be holding you accountable. I would walk in, I would put this in front of you. Please memorize these. They'll make your life so much easier at the end of the day. Okay? So something like sine of a plus b is equal to the sine of a, the cosine of b, and I'll put a plus minus here, plus minus the sine of b, the cosine of a. So if I apply that to this term right here, that means the sine of pi over 2 minus theta is equal to the sine of pi over 2 cosine of theta. Then notice I have a minus sign, so I take the minus sign here. You say sine of theta cosine of pi over 2. But sine of pi over 2 is 1. And cosine of pi over 2 is 0. So this whole rigmarole gives me cosine of theta. Let's do the other one. Okay. Cosine of a plus or minus b is equal to the cosine of a, the cosine of b. Now we have to be careful. It's actually a sign switch. The sine of a and the sine of b. Which means if I have the cosine of pi over 2 minus theta, that's equal to the cosine of pi over 2 cosine of theta plus, so notice I have the minus sign, which means I have to take the plus sign now, right? Whatever the bottom sign is, you use the bottom sign. So I have plus sine of pi over 2 sine of theta. And you say, well, cosine is 0. Sine of pi over 2 is 1. And so I end up with the sine of theta. Now, we could have geometried that out if we had gone a little bit differently. but I think that that's always a good review. So for our x component, we have just the sine of theta. And for the z component, we have the cosine of theta. Keep in mind, excuse me, we have to keep those negative signs in there. So negative sine of theta and negative cosine of theta, just to simplify the expression. Good so far? Cool. Let's go ahead. Let's keep going. Okay. We'll have to work on the DL. In fact, maybe we should do that next. How can you relate, if we're talking about an arc, a circular arc, how can you relate an infinitesimal length, DL, to the infinitesimally small angle, d theta? Yeah, right? This one we've dealt with too. In this case, DL, an infinitesimally small arc length, is r d theta. So at the end of the day, we have now turned the direction of our current flow into right now we've taken our generic DL and we've turned it into an expression for this problem. Well, shoot, now we should probably do something like DL cross R. Let's go ahead and do that. Okay. And sine theta, 0, negative cosine of theta. You've probably got it. You're way ahead of me here. What do we have? We have cosine of theta, y. Oh, excuse me. I'm going to keep those negatives in there. Negative cosine of theta, y, and sine of theta. And then I've just pulled out the common terms. We would still have an r that comes from this sucker right there. So call this y over r. And then we have an r d theta from the dl. So I'm going to just write this as r squared d theta for a second. Let's go ahead. We'll do the cross product. Well, okay, x's. Now we can start. We're going to start seeing we can do this a little faster. The x, there's a 0 there, so I get 0 x hat. Okay. The y hat, what do I get? I get plus y hat cosine squared of theta. Okay. How about the z hat? I get z hat plus z hat negative sine theta times y over r. But wait, there's more. Right now I got to go the other way. I get negative. And so what do I have? I have negative y over r times negative cosine of theta in the x hat direction. Okay. Then I have minus a negative sine theta times sine theta y hat. Oh, that's going to be nice. And then I get a 0 for the z. Excuse me, I should be consistent. We'll say minus 0 z hat. And you see, oh, that's nice. I have something like y over r cosine of theta x hat. You notice for the y component, I have a cosine squared plus a sine squared. Nice. So I just get a plus y hat. And then the z hat component, I get minus y over r sine of theta z hat. Now keep in mind, that's just performing that cross product. Excuse me, it's a terrible underline. That cross product, I still had this kind of floating around. So I should take this whole thing and multiply by r squared d theta. And similarly, I have this r squared d theta. Oh, bummer. Right, bummer. I've got 3 components now. I've got an x hat, I've got a y hat, I've got a z hat. So when I want to go to the law of Biot Savart, so we're not quite done yet. We're getting there. When I want to go to the law of Biot Savart, I have to do 3 integrations now. Right? I have the I dl cross. So I'll write it like this just to remind ourselves we actually are doing this right now. So I didn't do the unit vector. I said, okay, let's just cross it into the vector, and then I'll divide by an additional magnitude. So what do I have? Well, I have to do this 3 times. I have to do this if I want the x component, no vector, x component, then I have to do mu naught over 4 pi I, and let's look at the x component. Y over r cosine of theta. So I have y over r cosine of theta, and then I still have this magnitude sitting down there. Rough. Cosine of theta over r cubed. And I'll have to integrate this. And guess what we forgot again? We still have that r squared d theta here. So we have that r squared d theta. And I should ask, what's the limits of integration here? Yeah, you got it. 0 to 2 pi. Right? We want to go every single piece around that loop. Of course, we have by equals mu naught over 4 pi I. And the exact same thing. We have 0 to 2 pi. And now we need to look at the y component. Oh, good. Just y hat. So we have r squared d theta over r cubed. And fortunately, that's just the y hat, so we don't have anything else to go in there. Just 1. We just put 1 in. And we have bz. Mu naught over 4 pi I. 0 to 2 pi. Go back. You see the pattern. Negative y over r. So I have a negative sign in here. Negative y over r. Sine of theta over r cubed. R squared d theta. And there, oh goody goody, are the 3 integrals that we get to solve. Okay? Whew. I guess what we need to do, we better get this r vector. Okay. What is r equal to? Well, we had our relative position vector right here. So we better put that down. We had that our relative position vector was r cosine of theta, y r sine of theta, with appropriate negative signs. Ugh, man, this is going to be ugly. Ugly. Right? So let's go ahead. Let's get the magnitude of r. And in fact, I'm going to use this idea here that that's just simply r dotted into r and then square rooted. It just helps a little bit. So what is this? This is r squared cosine squared of theta. Oh, maybe this isn't so bad after all. Y squared plus r squared sine of theta. squared. You say, well, yeah, maybe this isn't so bad, right? Because notice again, I have a cosine squared and a sine squared. And so this whole thing just ends up being r squared plus y squared to the 1/2. Which means those r cubes, what I have to substitute in here is r squared plus y squared to the 3/2. Now, why do I mean, yes, it looks ugly. Don't get me wrong. But big R is a constant, just the radius of the circle. Why? Also a constant. It's the distance above the loop. So the upshot here is that these integrations just got wicked easy, right? Let's take a look at the x component one for a moment. What's our integration variable? It's theta. Constant. This is a constant. This is a constant. That's a constant. Everything's that's a constant. That's a constant. Everything's a constant, right? So what is this? What is this really? Well, I need to integrate from 0 to 2 pi cosine of theta, d theta. Quick, what's the integration? No. Do it off the top of your head. Different way to say it. What is the area underneath the curve for one complete cycle of cosine? And never mind the fact I drew sine. What is the area beneath the curve for one complete cycle, 0 to 2 pi of cosine? It's 0. How about this one? Right down here. Constant, 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 constant. The only thing that you have to integrate is sine of theta. So from 0 to 2 pi of sine of theta, d theta. Again, you think of, okay, this one I can actually draw. The area beneath the curve is 0. One full cycle, area beneath the curve is 0. Which means the x component of the magnetic field, 0. The y or z component of the magnetic field is also 0. That should make some sense. You're dealing with a symmetric object. The reason that these are 0 is because I put you directly above the symmetry axis. It's not by accident I chose that. Of course, this one, the middle one, that one's not terrible. All you're integrating, well, this is a constant. That's a constant. So you're just integrating d theta. You're integrating from 0 to 2 pi of d theta. Well, that just gives you 2 pi. No tricks there. And so we are almost home free. We have by is equal to mu naught over 4 pi I. Let's go back and look. We had something like big R squared divided by big R squared plus y squared to the 3/2. So again, I'm substituting in the value for little r. And then what else do we have? We've taken care of that. Oh, we still have to do the integration. So we have an additional 2 pi. So if we cancel, we've got this 4 pi, we've got that 2 pi. So we end up with something that says, above the symmetry axis of a current carrying loop, the magnetic field strength is given by mu naught I over 2 r squared plus yq squared to the 3/2. And this whole thing is in the y direction. So I'll go ahead and just do that. Put loop. Pretty cool, huh? And you say, why would I ever need this? I'm never going to run into a current carrying loop. Well, okay, you could argue that. I say, oh, nay. Let me give you a quick example, and then we'll call it quits. Okay. Imagine for a moment an atom. The electron is whizzing around the nucleus, and I'm going for the Bohr model here. You have the electron moving in a circle around the nucleus. That electron is essentially a current, right? You have a charge which is moving through space that generates a current, which means the motion of this electron around the atom is generating a magnetic field. And if you're directly above it, right? If you're directly above that current carrying loop, this would be the value of the magnetic field. Right? A different way to think about it. So if I go, this is the overhead view. If I go for a side view, let's say that the current is going in on this side and coming out on this side. The magnetic field directly above, so the magnetic field directly above will be in the positive y direction, going like this. And in fact, below as well. So you'll have the magnetic field directly on that symmetry axis is going up. You say, what happens if you get off of that symmetry axis? Say you're over here, your field point's over here. You'll actually find out that it's going like it angles. And in fact, I'll go a little bit further here. For a current carrying loop, you'll find that it actually angles around and goes. And it will look, okay, you don't need me to draw more. It will look like a dipole field. Okay. That's where you get that. I'll put up a picture. Boom, there. Now you have a pretty picture instead of my crappy drawn picture. Okay. So this is the start of that. Okay. I just want to give you a little flavor for how, for example, atoms, you can think of an electron going around in a circle as a current. Because of that current, you can take this atom and model it almost like it were a bar magnet. Notice you can model this as if it were a north magnet and a south magnet. And then you have this dipole field. Cool? Okay, I'll leave you there. I'm sorry it's a little long, but just a couple of examples and some calculus thrown in. Hey, thanks for your attention. I'll see you next time.